Okay, think about this for a second. Every single year, we generate just, mountains of textile and electronic waste, enough to fill skyscrapers.
It's staggering, really.
And the really shocking part, less than a quarter of it, maybe even less, actually gets recycled or reused.
Yeah. So let's dig into why this is something you should really be paying attention to.
Mm-hmm.
Today, we're doing a deep dive into the idea of circularity for smart products. Specifically, these new textiles that have flexible electronics woven right in.
Right, the e-textiles.
Exactly. And we're basing this conversation on some fascinating research from Sensors 2025, a specific paper that looks at the challenges, the opportunities, the whole picture.
And it's crucial because we're not just talking about, niche gadgets anymore. This stuff is moving into everyday items. Think clothing, wearables.
Literally the fabric of our lives, potentially.
Precisely. And how we deal with these things when they wear out or we're done with them. That's going to be a massive factor in sustainability overall. Couldn't agree more. So whether you're someone who loves keeping up with the latest tech innovations, or you're really focused on environmental issues, or maybe you're just curious about what your clothes might do in the future, this is definitely for you. Think of this as your shortcut, your way to grasp the key takeaways from this dense research without, wading through the whole academic paper yourself.
Yeah, we're boiling it down.
Our mission today is pretty clear. Pull out the absolute must-know insights about making these incredible smart textiles and electronics genuinely sustainable, truly circular.
Because the old way, the linear model, take, make, dispose it, just doesn't work. Especially not for products this complex. It's just fundamentally unsustainable.
Okay, so let's get into the exciting stuff first. Smart textiles. For anyone maybe not totally familiar, what exactly are we talking about? Can you break that down?
Sure. So imagine fabrics, actual textiles, but they have electronics integrated into them. So they can sense things in their environment or about the wear. They can react, sometimes even adapt. People call them e-textiles, electronic textiles, smart textiles.
Giving clothes a kind of digital nervous system.
That's a great way to put it, actually.
Yeah, sounds very sci-fi. But these are real now. What are some examples we might see?
Oh, definitely real. We're seeing them in healthcare, for instance.
Yeah.
Shirts with sensors woven in that track your heart rate, your breathing, maybe other vital signs continuously.
Wow.
Then there's interactive clothing in fashion things that can change color, display patterns, even fabrics designed to harvest a bit of energy, maybe from your movement or sunlight.
Okay, so healthcare, fashion, any other big areas?
Sports, definitely. Yeah. Tracking athlete performance in real time. And military applications, too. Monitoring soldiers' vital signs. Camouflage that can change or adapt. Integrating communication systems. It's a really broad field.
It really is. So what are the magic ingredients? It's not just cotton thread with a chip glued on, is it?
No, not quite. You need special conductive materials. Think really fine metal fibers. Silver, copper, sometimes gold or conductive polymers, even carbon-based materials like graphene or carbon nanotubes. These act like the wiring within the fabric itself.
Okay, so conductive threads. What else?
Then you need the actual sensors, detecting temperature, pressure, maybe chemicals, biological signals. You need a power source, so flexible batteries or maybe tiny supercapacitors. Some are even exploring energy harvesting within the textile and flexible circuits to connect everything together.
Right, got to connect the dots.
Exactly, all integrated into the textile structure.
How on earth do they get all that delicate tech into the fabric without wrecking it?
Well, there are a few clever ways. Sometimes they use printing techniques, almost like screen printing a T-shirt, but using special conductive inks.
Right.
Or they adapt traditional methods, weaving or knitting or even embroidering, with these conductive yarns right alongside the normal yarns.
So built right in from the start.
Exactly. And then, crucially, they often use lamination or encapsulation, basically sealing the electronics to protect them from, moisture, washing, general wear and tear, makes them more durable.
Makes sense. Okay, so we've got this super innovative field, really exciting potential, but like we hinted at up front, this brings us to the big problem, waste.
Yes, absolutely. That linear take, make, dispose thinking just crashes headfirst into the reality of these complex products. We're already drowning in waste, globally speaking.
Can you give us a sense of the scale? The numbers are usually pretty sobering.
They really are. Back in 2019, the world consumed something like 95 billion metric tons of raw materials. Just consumed. And electronic waste, e-waste.
Yeah.
In 2022, we hit a record 62 million tons. That's projected to be over 80 million tons by 2030.
And that's just electronics. What about textiles?
Another massive stream. Around 92 million tons of textile waste annually. And with fast fashion and changing trends, some predict that could jump by 60% by 2030.
Those numbers are just hard to even picture. And recycling rates are still terrible, aren't they?
Dismal is the word. Less than 10% for plastics globally. Textiles are a bit better, maybe around 25%, but still, the vast majority ends up landfilled or incinerated.
Which causes its own set of problems.
Big problems, especially when you throw smart textiles into the mix.
Right. What are the specific dangers when these complex items get thrown away improperly?
Well, the electronic bits often contain hazardous stuff, mercury, lead, cadmium. These can leach out into the soil, into groundwater, contaminate whole ecosystems. It's nasty stuff.
Can the textile part?
That can cause issues too. Heavy metals from dyes, plastic polymers shedding microfibers, even materials like graphene. While graphene itself is quite stable, its long-term effects aren't fully known and it can persist. Plus, under certain conditions, some forms might release toxic compounds. The cadmium from just one discarded smart wristband, for example, could potentially contaminate thousands of liters of water. Makes you think.
It certainly does. So clearly, moving to a circular model isn't just a nice to have, it's essential. But it's not easy, is it? What are the big roadblocks for smart textiles?
No, it's definitely not easy. One of the biggest challenges, as the paper highlights, is just the material complexity. You've got fabric, maybe multiple types, then tiny wires, sensors, chips, maybe a battery, all bonded together, often sealed for durability.
They're pulling them apart neatly for recycling is tricky.
Extremely tricky. Often they're designed for performance, not for disassembly.
Okay, complexity. What else?
Well, we mentioned the hazardous substances in the electronics that complicate safe handling and processing right there. Then there's a real lack of standards and regulations specifically for these textronic products.
Right, they fall between the cracks.
Exactly. Current laws for electronics or textiles don't quite fit these hybrid things. There are loopholes. We really need new standards for design, for manufacturing, that actually factor in recycling from the get-go.
So the way they're made is part of the problem, too.
Often, yes. These advanced manufacturing processes, they create amazing functionality, but easy disassembly? That's often not the priority. Plus, sometimes the electronics, like the battery or a sensor, might fail long before the actual garment wears out.
Ah, so the whole thing gets binned because one tiny part died.
Precisely. Leading to premature waste.
And what about us, the consumers, and the companies making them? Is awareness an issue?
It definitely is.
Yeah.
Often people just don't know what to do with these items at the end of their life. You can't just toss it in the clothing bin usually, or the e-waste bin either. And the systems for returning them, for collecting them separately, they're really underdeveloped right now.
So no easy way to do the right thing, even if you want to.
Largely, yes. And on the producer side, there needs to be more focus on designing for longevity, repairability, and ultimately recyclability.
You mentioned specific regulatory headaches, too. Can you unpack those a bit more?
Sure. The fact that you're mixing organic stuff, cotton, wool, whatever, with inorganic electronics, that itself is a nightmare for existing waste regulations. Which box do you tick?
Right.
There's no consistent international framework for recycling them. Classification is messy. Is it e-waste, textile waste, something else? Then you have things like extended producer responsibility, EPR schemes, where manufacturers are financially responsible for end of life. Those aren't really widespread for smart textiles yet.
Okay.
Plus, chemical regulations like REACH in the EU, which restrict certain substances, those apply and can make recycling processes more complex too.
It sounds like a tangled web.
Yeah.
And just the physical act of separating everything.
It's a huge technical challenge. Getting those tiny wires, sensors, batteries, displays out of the fabric, especially when they're bonded or laminated in, very difficult. Batteries are a particular issue. They absolutely need separate, specialized recycling because of the chemicals.
And knowing what's even in the garment in the first place.
Another big problem, lack of standardized labeling. You pick up a smart garment. How do you know exactly what materials are in it? How should it be recycled? Without that info, efficient recycling is basically impossible. And finally, the economics.
Oh, yes, the money.
It costs more to separate these complex items. So there often aren't strong financial incentives for recycling companies to invest in the specific tech needed, especially when the market for the recycled smart materials is still pretty small.
Okay, wow, that's quite a list of challenges. But it's not all doom and gloom, right? The research must offer some solutions, some ways forward.
Absolutely, it does. And a central theme is design for circularity. basically thinking about the end of the product's life right from the very beginning during the design phase.
Making it easier to recycle from the start. What does that actually involve?
It means choosing materials, carefully prioritizing biodegradable ones, or ones that are easily recyclable, or using recycled materials to begin with. A really key idea is modular design.
Modular, like clipping the electronics in and out.
Exactly. Designing it so the electronic components can be easily detached from the textile part, snapped on, maybe zipped in, something reversible. That way, you can treat the electronics and the textiles separately at end of life. The paper actually had a figure showing this kind of concept.
That makes so much sense.
It also means minimizing toxic chemicals and avoiding materials that are just really hard to recycle, like certain blended synthetic fibers that you can't easily separate, and setting up systems for people to actually return these e-textiles easily.
We're seeing some fashion brands already using more sustainable materials, aren't we?
Definitely. There are companies like Pangaea using recycled fabrics, even materials made from algae. The goal is materials that can biodegrade safely or be easily recycled. And they're thinking about how to make any tech components removable too.
So if you can separate them easily using that modular design.
Then it becomes much more manageable. The electronic module goes into the e-waste stream for metal recovery. The textile part goes into textile recycling, maybe mechanical shredding for fibers, maybe something else.
Okay, design is key. What about the actual manufacturing process itself, the production phase?
Right, sustainable production. This is about reducing the footprint during manufacturing, using resources, energy, water, materials much more efficiently, minimizing waste created in the factory, using recycled materials as inputs whenever possible, switching to renewable energy for the factories.
Any companies leading the way here?
Well, a well-known example, though not specifically just smart textiles, is Adidas's work with Parley for the Oceans.
Using recycled ocean plastic for shoes and clothes.
Exactly. Taking waste material and turning it into new products. Imagine applying that thinking more broadly to the polyester or other synthetics often used in smart textiles. The research paper even included a visual showing how sustainable production methods could significantly cut CO2 emissions, waste, and water use. It's achievable.
Okay, so better design, better production. What about making the products we do make last longer, the use phase?
Absolutely critical. We need to extend the useful life of these things. That means designing for durability, yes, but also for repair and maybe even upgrades.
Upgrades, how would that work?
Think replaceable modules again. Maybe the sensor technology improves or the battery degrades. If you can just swap out that small module instead of replacing the whole garment, that's a huge win.
Makes sense.
Educating users on proper care helps too, obviously. And then there are different business models, things like rental services for specialized smart garments, manufacturer-supported repair programs, those return or recycling schemes we talked about, all keeping the product in use or the materials in circulation for longer.
Like Patagonia's repair program, maybe adapted for techie clothes?
Precisely that kind of thinking. Offering battery swaps or sensor upgrades could make a big difference. Interestingly, the paper notes that manufacturers aren't always required to state the expected lifespan, especially for components like batteries. They mention Hexoskin specifying battery life for their shirts, but point out it's not standard practice. Knowing that lifespan would help everyone plan better.
Good point. Okay, so eventually, even with repairs and long life, the product reaches its end. What about end-of-life management?
This is where we need the infrastructure to actually collect these things, effectively convenient drop-off points, maybe take-back schemes, and then, crucially, efficient recycling processes to turn both the textile and the electronic components back into valuable secondary raw materials.
Recovering the value.
Yes, and investing in the technology to separate the components without degrading them too much. The paper mentioned Fairphone's modular phone design.
Right, designed for easy repair and component swapping.
As sort of an inspiration for how textiles could potentially be designed for easier end-of-life handling. The paper had tables summarizing different recovery processes like mechanical shredding for some textiles, precious metal recovery from the electronics, even composting for biodegradable parts. And another table comparing recycling methods.
Where you mentioned mechanical, chemical, biological. They have pros and cons.
They do. Mechanical is often cheaper, lower impact initially, but might damage fibers and struggles with separating complex bonded materials in smart textiles. Chemical recycling can recover more, separate better, but it's often more expensive, energy intensive, and can have its own environmental impacts depending on the chemicals used. Biological methods, like using enzymes, are promising for biodegradable parts, lower impact, but perhaps less efficient currently for the broad range of materials.
And just getting the used items back, the reverse logistics.
That's fundamental. You need easy collection networks. maybe incentives for returning items like H&M's clothing take-back program, but adapted for textronics. The paper had a diagram showing this flow. It also noted that while general textile recycling is growing, smart textile recycling is still very niche. Companies like Worn Again Technologies or Circ are working on advanced methods, but it's early days for complex smart textiles.
Which brings us back to the economics. Is recycling the stuff actually profitable, or is it still mostly a cost?
Yeah, it's complicated. Right now, with the extra steps for separating electronics, the limited market for the recycled output, regulatory hurdles,
Yeah.
it's often not clearly profitable on its own.
Right.
But there's value in recovering precious metals from the electronics.
Yeah.
That helps offset costs. And crucially, if products are designed for easier recycling from the start, that modular idea again, it could dramatically improve the economics down the line.
Okay, so it's challenging, but there are paths forward. Looking ahead then, what are the key future directions highlighted in the research? What needs to happen next?
Several key things. First, developing standardized guidelines for design, for labeling, for recycling methods. Imagine QR codes on labels telling you exactly what's in it, how to recycle it. That would be huge.
Standardization, okay.
Second, really investing in and scaling up those innovative recycling technologies that can handle these mixed hybrid materials effectively. Think advanced chemical separation, maybe specialized plants.
Technology developed?
Third, much more collaboration. Across sectors, manufacturers, recyclers, policymakers, researchers need to work together, share data, develop solutions jointly, break down the silos.
Makes sense. Collaboration.
And finally, continuing to explore and develop new materials, especially bio-based and biodegradable options, even for the electronic components themselves. Biodegradable sensors, circuits from plant fibers. That's the ultimate circular vision, perhaps. The paper wrapped these up nicely in a final figure.
It really feels like this needs everyone pulling in the same direction. The paper mentions institutions having a big role, too.
A critical role. Public institutions, government ministries, environmental agencies, both nationally and internationally, like the EU Commission, they need to create the right policies, the right incentives. NGOs like Greenpeace or the Ellen MacArthur Foundation are vital for advocacy and pushing for change. And the private sector has to innovate and implement.
And academia.
Crucial for the research, for developing those new technologies, for educating designers and engineers, and for raising public awareness. Building those bridges between research and industry, too. It really takes a concerted effort from all these players, supportive regulations, new tech, and public education.
So wrapping this all up, our deep dive really underscores this double-edged sword, doesn't it? Smart textiles are amazing, full of potential.
Absolutely incredible potential.
But they also bring some serious environmental baggage if we stick to the old linear take, make, dispose way of thinking.
Precisely.
Yeah.
Moving towards a circular economy isn't optional for these technologies. It's fundamental if they're going to be truly sustainable as they become more common. And the research shows there are promising ways forward, better design, smarter production, longer use, effective recycling.
But it requires real commitment.
Real commitment across the board, from design right through to end of life.
And that really brings it back to you, listening to this. As you encounter these smart textiles more and more, understanding the backstory, the environmental implications, and the importance of this shift to circularity is, well, it's pretty crucial.
It really is. And maybe it leaves you with a final thought to chew on. Imagine that future, where your clothes aren't just things you wear out and discard. Imagine they get updated, repaired, and then at the very end, responsibly returned and recycled back into new materials. How might that fundamentally change your relationship with technology, with your belongings, and with the environment itself?
A fascinating picture of what could be. Thank you so much for joining us on this deep dive today.
My pleasure.